Good morning, everyone. We're going to get started with our first team. We've got the first two teams lined up, but after that, decide amongst yourselves who wants to go up next. We start off with the team comparing forecasting on sky localization of individual sources to Bayesian analysis, and then after that, we've got optimal statistic significance forecasting. After that, it's up to y'all.
Charger.
But we'll give the teams, let's aim for a maximum of 15 minutes. Take a few minutes for questions and move on after that.
Can you not plug into this one right here?
So I think the best thing is to connect on Zoom.
Yes.
And then just share from there.
This is all for your PC and this will fit.
So this is. Thank you.
Really do not endorse this.
Okay. Here's the, where's this one? This.
Including. Lucas surgery going off.
Sorry.
We're complaining that things not working. He's like, wait a minute, this one did work.
Okay. Content of this meeting is being shared to show everybody. Show me, shut up, dude. All right, let's go. All right, everybody. Excuse me. All right, so yeah, we're team efficiency. Hopefully you get what that means by now. We're comparing single source localization with the Fisher formalism versus a Bayesian approach. Okay, yeah, we got our team
I
members.
did not
Liana-
endorse this.
Yes, she did. She asked for it specifically. She,
Yeah.
yeah, she demanded that we put
She
Supreme
accepted
Team
the
there.
dictator.
Yeah, but yeah, this was our project. So we're gonna talk a little bit about it. A lot of struggles, so we'll also talk about that. Initially, we thought, okay, we're just gonna start out by learning the Fisher matrix. We'll read some of the literature on localization and we'll just run quick CW and then we'll get some nice results. We'll be able to compare the two, see if they converge, see if there's a nice easy calibration factor. That didn't end up happening. It was a lot more complicated than that. I'm gonna talk about my path, figuring out the Fisher formalism and working on building a machine to like get localization areas with Fisher first, and then they'll talk about quick CW and their journey with that. But yes, first we reproduced some results from a recent paper that showed like localization area for a different pulsar configuration. We got that, which was very nice. Then we built a Fisher localization demo, which we'll show you later. Very cool. Then everything broke, and we figured out that there was a lot of bugs in the code. Then we fixed them, which was really nice. And then everything broke again. But at the end of the day, we have a kind of working Fisher demo, which we're gonna show you at the end. But that was kind of the journey there. I can talk to you way too much about the math of Fisher matrix, but it's probably too boring. The demo is a very cool addition. But with the demo,
Okay, so next thing after Sebastian done the Fisher matrix formalism, we started to think how to do it in the Bayesian process. So first we tried to learn the quick CW, but in quick CW, we have seen first the 2024 VIPER quick CW codes and tried to amplify that. But we have seen that it's not that easy. It's become slow CW from the quick CW. So I figured why not just run a normal MCMC from the pulsar data of the 12.5 year and injecting a gravitational wave source and just getting a fake TOA, and from there just MCMC analysis on two parameters, just the sky localization. So I did that, and this is our corner plot for the cos theta and phi for just an MCMC chain with injected signal. Then Sebastian also did the Bayesian process, but with the grid method, and we see though we injected same thing in our source, we are getting different results. So we sit down and started to debug, and after 2 hours of debugging, we figured I have mistaken the megaparsec as kiloparsec, and then our code is working, and we got something at last, which also now, and they work with the PTA replicator, and it is the worst thing of all time. Niana will tell about that more, I think so. And Quick CW running on realistic TOS, so Niana knows much more about that than me.
Those were not also my words. Someone wrote those, but,
Oh. No, wait.
Maybe reload. Oh, no, okay, that's like the important plot, okay, wait, hold up.
was crashing.
This is like
That's the point.
the important.
Yeah, that's the only.
No, you got it, please look, this, okay, we're gonna do
Okay.
it like this, cause this is like the plot that we made.
Okay, so our main purpose of our project was to compare between the feature and the Bayesian process and check it in different SNRs, how the sky localization area behaves with both the process. So as we can see here, the blue dots are for the Bayesian plots and the red ones are feature ones. So for feature one is always behaves like 1 by SNR square because it's give a very lower bound even in low SNR, but for the Bayesian, as we can see, we fitted it with 1 by SNR square, but it doesn't go with that. It blows up at the low SNR. So it gives more, the feature gives more optimistic data at low SNR, but the Bayesian gives a more accurate value for the sky localization area. But also, like in the high SNR, you probably assume that it's going farther away, but it's not. We have seen that it's actually merging after 150 or 200 SNR. So that's our main plot. That's our main result. And also we have learned how to plot the sky localization maps from Paulina's code. And this is the sky localization for SNR 5, which is bigger. And this is the for SNR 20, as you can see in the bottom. So that's smaller, and this is 68% credible region. And that's what we did with the MCMC, fake MCMC. And now I'll hand over to Niana to talk about Quick CW.
I'm gonna hand it over to Alan first.
So I did a lot of the quick CW stuff, which as you heard earlier is not exactly as quick as you'd think it would be. So the first issue that I had to deal with was we wanted to compare all the methods, so we needed our simulations to be the same. But as you also heard, PTA replicator sucks, so it was sort of hard to do that. And so the way that Sebastian and Surjit ended up doing these simulations was not creating par and tim files. So my first step was to sort of edit a version of that to create the par and tim files, which we needed for Quick CW. And then I did that and tried to run Quick CW, and it took forever and gave bad results. So I was going to try to do a similar sort of cheating method of just setting some of the continuous wave parameters like the chirp mass and the distance and inclination and some of those things to be constants instead of a prior region, just to kind of quicken it up. And it turns out there's no really easy way to do that except for actually going into the Quick CW source code and changing the priors in there. And if you set them to constants, you get a bunch of error messages back. So to try to still sort of do this, I just turned them into really tiny priors, which helped a little bit, but still doesn't quicken it up all that much. But then it ran at least. So we were able to run Quick CW with the same simulation. And did it work? I would say no. Is there a corner plot? Yes. Did it run? Yes. Did I have error messages? No. So did it run? Yes. Do the results mean anything? I mean, the couple pixels you see are vaguely close. So who knows? Don't think that's paper worthy, but who knows? So it really needed more computation time. I looked at the actual Quick CW paper, which says it ran for several days each time on a chip that costs $2,000. I was running this for several hours on my computer that costs less than $1,000. So the real thing with Quick CW is it quicker than some of the other methods? Probably, if you slam it at a supercomputer, which I did not do. So that would be sort of, if you wanted to use Quick CW and have it be actually quick, I'd recommend slamming it at a supercomputer and letting that sort of be a lot of the quick process. as what I ended up doing, was not that quick and didn't really find any CWs. And now Niana will tell you a little bit more about
Yeah.
quick CW struggles.
Come on up here.
All right. I had grand plans when I joined the summer school. Okay, so my contribution to this project was mostly satisfying my fixations. I developed a fixation that was I want to use as realistic TOAs as I can find. And the best way to do that is to download the real data and use it. And then someone said PTA replicator, and I was like, oh my God, easy, fancy, nice to use. PTA replicator alone can take over an hour to load your par and temp files if you use like 45. Oh, Kyle's nodding, thank you. I feel very validated. And supposedly it's a fairly straightforward way to simulate data. You can inject signals, red noise, continuous waves, anything you want. But it was taking too damn long. But I was determined. I was gonna make this boy work. And so I spent a good chunk of my time trying to come up with ways to make it run faster. I will have you know that if you use the standard settings, if you just take the example notebook and run it through, you will have to wait 1.5, 2 hours, possibly more, to even get the data set you need to kind of give to QuickCW to do the Bayesian analysis. So what I did do, this was partially Steve's idea, was to downsample the TOAs, because many of these have like over 1,000, some up to 10,000. I might have seen a 20,000. And so they were taking too long to load. And so what I did was downsample those. And because I realized that I can no longer operate in the realistic realm, I reduced the error bars to 50%, which, as you can see, is still fantastic. And then, do not laugh. This is important. Right. So, why did I do all of this? I think I kind of lost the motivation for why I started this fixation in the first place, but it was all because if you want to use QuickCW, you need to create an enterprise Pulsar object. And the only examples I've seen start with par and temp files or some version of the real data format, and then you can create the par and temp files, the Pulsar object. But with my downsampling, you no longer have to sit for 2.5 hours. It'll be 3 minutes. So I think that is success on my part. What is also a success is that if I take just 20 pulsars and ran it through QuickCW, this is a massive success. We should be looking at the whole sky anyway. So, yes. Thank you.
That's how she's the supreme leader.
Okay. Yeah. All right, and then real quick, guys, I'll show you the demo that I was talking about. So basically, if we can see here, we just have a little mo-wide plot. Oh,
Wait.
hold up. I got it. Okay, so we have a little mo-wide plot. We have a bunch of pulsars across the sky, and we have a gravitational wave source. And basically what this little interaction allows you to do is change the SNR of the source and see how the sky localization area, as predicted by the Fisher matrix, changes. And you can move the source and you can randomize the pulsars. You can add in, okay, this is a good demonstration actually. We can see that if the source is around a lot of the pulsars, the localization gets a lot better, right? But if you move it somewhere where there isn't any pulsars, localization is a lot worse. We see the scaling with the signal to noise ratio. And this little slider is the uncertainty on your pulsar distance. Right now I have the pulsar term switched off, so it won't impact that at all, but you can also go into the code and switch the pulsar term on, and you'll see that as you increase the uncertainty on your pulsar distance, your localization becomes a lot worse. You're relying entirely on an antenna response function, which is your proximity to certain pulsars, to help you with localization. If your uncertainty is much smaller, then you can, I forget the exact term, Steve could talk to you about this, but it's, you can use interference based on your pulsar distances, how the gravitational wave phase changes between your pulsars and you to help with localization. But this is a fun demo. Hopefully I'll share it one day. Maybe it'll be good enough to share. You can do it with nanograv pulsars, but right now it's still a little bit buggy, as you can see. So we got to fix some things, but either way, it's a cool demo. So hope you guys enjoy. Yeah. Any questions?
Where are you going?
Lucas?
I have a couple questions, but firstly on the demo, are you able to change the number of pulsars?
Yes, right now you have to go into the code to do that, but I can add a slider so that you can add it.
I think it'd be cool to do like two pulsars and like drag it between them and see like how the circle like just, you know.
Yeah, yeah.
Okay. Another question was, could you go to those, like, the big slide where you have the three plots?
Yes. Let's go there.
But you have
Uh-huh.
to exit, oh, it's what, it's.
Yeah.
Yeah.
Okay, I don't know like anything about any of this.
Yes.
Yes.
But for the like localization you show on the top right image, yeah, that.
Yes,
So, like, so when I'm looking at the circles or like how, like we would estimate the localization of the source, correct?
yes.
Yes.
So why do they like converge it on the middle? Like that seems like I would know exactly where the source is.
It's-
That's interesting. So it's because this source is right next to one of the nanograph pulsars.
Yes,
And
Oh,
you can see the antenna response function around that pulsar. It's literally like a little X.
Gotcha.
So yeah, that's why this is next.
Okay,
If you were to put it where there are no pulsars, it would be more like.
more, yes.
okay, gotcha, that makes a lot of sense.
Yeah.
Thank you.
Yes, Colin?
These sky localizations look really good. You're doing something actually good.
Well, these are still really big. I think like, yeah, 279.5 degrees
Yeah.
squared. That's,
But that's a realistic. I thought we were like hoping that they would.
Yes.
Degrees.
That's fair. This one is really close to a pulsar. That might be a reason it's smaller. Also, in running MCMC, we fixed all the other parameters besides sky location to the correct values. We only let the MCMC iterate over sky location. So you can imagine if you accidentally have a mismatched frequency or mismatched chirp mass, you might assign that gravitational wave to a different part of the sky. So your area widens a little bit. That's also probably a significant reason why these look more clean than the ones you've seen before.
I think it's also worth adding that the actual residuals were almost clean, beautiful
Yeah.
sinusoids
Yeah.
without noise.
There are
Yeah.
no noise.
That's right.
Yes.
Yeah.
That's also, yeah. Yes.
Yeah.
Yeah, Steve?
Just a comment that I'm not surprised about the issues with quick step fusion. It's, it's not as user friendly as enterprise, so it uses the bones of enterprise and more modules, but it's written in a more, I think it requires more, experience to set the different functions. And there are newer codes coming out anyway that might be more user friendly, so I'm not surprised. I'm a little bit surprised that it was not converging to correct values, because it is supposed to be so fast. Again, I'm surprised that it's become quite slow to run. So these are useful things for us to know.
Sorry, what is fast by your definition?
Well, I would expect an analysis of the scale that we're talking about to take order a day.
Oh, I ran it for 15 minutes.
Okay.
Yeah, mine was
It's
one hour.
realistic data.
Yeah.
Many TOAs deal with that. Now, I would say it to take about a day first.
Mhm.
That's changing, so there are newer codes that use GPU, companies out like less than an hour.
Just to leave you guys with that. Alright.
That's the purpose, well done.
Yeah, thank you, thank you.
Oh,
They didn't talk about, well, this is very good. They said both.
Wait, you think this time? Starting this up? Yeah, you can. Okay.
Can I just share the whole desktop, or are you saying no, nation? I think you have to do the whole desktop in order to go into slideshow mode, because it screws up, I think. Yeah, but you can look at this for Windows if you need to, right? I can set a title if you want.
Okay, go ahead. All right. Hello, everybody. We are very concentrated on this side of the room. I'm just noticing that up here. Okay, so, yeah, thank you, Alexander, for holding down this show. We are the team that's doing the effects of the detection parameters on the optimal statistic p-value for PTAs. So, yeah, we have a plan that we'll show in a little bit, but foremost, we're gonna go through a little bit of background because that's good practice for us. And then, the background will take you through optimal statistics stuff, which, hopefully you remember from Kyle's straight talk. And then some p-values and GX2 stuff, and then actually results in plans. So I'll let Tejas kick us off with some background.
Okay, well, so essentially the whole point of trying to get the optimal statistic is to, well, the whole goal is to find detect gravitational wave background, and we need a way to explain how significant our detection is. And so one way to do that is to create the pairwise estimator, the rho AB, and that is related to the gravitational wave amplitude by taking its expectation. Yes, and then we compare it against what the null hypothesis would be if it was 0. So I have a slight derivation. I took everything from Kyle's paper. So essentially, when you write out the likelihood, you have the covariance matrix up on top, and you have a bunch of submatrices that's basically correlating the residuals with one another. So for example, SAB, which is one of the submatrices, is the residual A, is the expectation of residual A times the residual of B. And according to the Wiener-Khinchin theorem, what we can do is we can take, because it's an autocorrelation, because we're correlating the residuals with itself, and this is a stationary process, what we can do is we can rewrite those submatrices as a power spectral density matrix in the Fourier space. And so that's essentially what's been done there. And as it turns out, we pull out a gamma term, which is what the Helms and Downs correlation is for those pulsars. And then with what Kyle had shown earlier a week ago, you can write out the estimator for that correlation between the pulsars. And essentially, the S hat there is essentially is where we've taken the SAE and we've taken out the Helms and Downs and the power from the power spectral density from the file. And so what we do is we create the statistic and we try to normalize it. And we set the expectation to be the Helms and Downs times the gravitational wave background. That's the way we set it up. And when we do, we kind of get just the trace of the original the pulsar correlations. Yes, and then we compare this against a null hypothesis. So the null hypothesis is assuming that there is no correlation. That means the pairwise estimator is 0. And and then we define a new gravitational wave background amplitude estimator based upon the previous stuff, and then we look at its variance. And yeah, and then you can also derive the estimator, the gravitational wave background estimator, amplitude estimator by minimizing the chi-squared. If you take the derivative with respect to the amplitude background. Yeah, that's okay. So on to Will.
All right, let me see. All right, so following what Tejas has said here, the optimal statistic is what gives us an estimate of the gravitational wave background. And to find how significant that estimate is, we need to calculate the signal to noise ratio, which I think we're all familiar with at this point. And then we use the signal to noise ratio to calculate the p-value, which tells us the probability of observing an SNR due to random noise instead of a detection. Hasboon and collaborators showed that p-value should be calculated using a generalized chi-squared. Let me see, yeah, go back down for that. So what's the problem here? We have to think about how this signal to noise ratio is distributed. So the old assumption is actually just a normal Gaussian distribution, but once again, Hasboon showed that we should use a GX2. And the figure that we see here shows that the GX2 prediction matches real data much better than a Gaussian. This matters because the wrong distribution equals detection appearing more significant than it really is. So our plan. So we're going to begin by simulating many pulsar timing arrays using PTA replicator, which I know a lot of you guys are familiar with. It takes the pulsar parameter files and customize time span, cadence number, and pulsar timing errors. Inject a gravitational wave background. Hold all other parameters constant while changing our time span, which Lucas will talk about. Simulate multiple realizations per time span, calculate optimal statistic in SNR, and then calculate the p-values, right? And then we're gonna plot those versus time span.
Let me take a, okay.
Yep.
So, I want to talk about our reality. So first day, we got zero work done. We didn't do anything on the first day. We spent the entire day, watching PTA replicator versus Tejas' laptop. It took like, I think it took 4 hours for him to get the software actually like installed and working for some reason. I don't know. I'm never using UV again outside of this, outside of the summer school. I'm just I'm con to everything. So moving on after that, we day 2 was actually pulsar simulations versus William's kernel. His laptop, the kernel on his Jupyter notebook crashed every single time he tried to run just any singular pulsar simulation.
It still crashes.
Replicator. So this was a collaborative effort. All 3 laptops put the power combined was required for this. So it really was. So day 2 was we were trying to figure out if we were going to be able to do this with everyone's laptop or just one. Finally, day 3, things were starting to look up. Tejas got PTA replicator installed. It only took 3 days and it was installed and working. Unfortunately, at the end of that day was the last time we saw Tejas. He took his leave. So day 4 and 5, we got a little bit of work done. Do not confuse work getting done with results being output. Okay, so what I mean by work getting done was that we simulated some pulsars. Yay. You know what you got to do something with them if you're going to simulate them. So I realized now on day 4 that simulating the pulsars was more computationally expensive than I thought. I had done some of these simulations with PTA replicator before, for like 15 or 30 pulsars. Like if you want to go higher than 30, like Niana was saying, it's like it takes a long time, especially for us because we were doing 10 different arrays and 10 different realizations of each of those arrays. So that's actually 100 arrays of 30 plus pulsars. And so when I tried to do that on my computer, it was successful, but it took 1,300 minutes. So it was about it was over 24 hours is what it took for my computer to finish, but it did finish. However, we didn't even end up using the data that gave me. Okay, so I then moved our simulations to Acre, and I was like our computing cluster here, and I was able to parallelize it so that I didn't have to wait for one array to finish before I started the next simulation. And so I could do all 100 simulations all at the same time. So then it only takes the time it takes for one simulation to run. So it actually only takes about 10, 15 minutes to simulate all 100 arrays. So that was really nice. Then we were starting to cook. Okay, we were able to actually start to do math after the simulations were pumping out. So then I tried to calculate the p-value because after these quick simulations, we had some data. I chucked it into Discovery. Discovery has a generalized chi-squared CDF function. So after you calculate the SNR, you can just plug it into that. It gives you the CDF, and the p-value is 1 minus the CDF. So I did that, and the GX2 CDF failed immediately, and it didn't work for about an entire day. And so we realized that, that we were gonna need to approach this from a different angle to get p-values and actually have results. So I thought maybe my pulsars were just bad pulsars because my par files, I removed all the backends from my par files because I wanted very simple pulsars and I wanted them as simple as possible so that I know exactly like what parameters I'm controlling. I thought that was smart. Okay, so I removed all the backends and then when this didn't work, that was my first guess was that the backends maybe was causing, or Kyle actually helped me and said maybe the backends are an issue. And so I took the entire night and added backends back to every single pulsar over the 100 simulations. And that took a while to figure out how to do. It's very simple, but it took me a while. And after I did that, I tried the p-values again and it still, it still didn't work. So then the next day started, and as was spoiled, it was the return of pages. He finally comes back after his presentation and actually he didn't miss anything. For all this time, we still had no, and we had no pulsars. So anyways, day 8 or the continued last of day 7, we actually successfully got simulations. The backends didn't matter at all. I was able to fix the p-values. It was a problem with the timing model in discovery. So we actually got some data. All right, so these are our results. So you're probably asking yourself, why do these look so god awful and have no shape or pattern in them whatsoever? That's because they actually aren't even time span being varied across the pulsars. So accidentally in our simulations, we were changing the start and end date of the observations, but keeping this was accidental. We were keeping the number of TOAs constant. So it actually was not increasing the amount of data. It was just changing the cadence. And so maybe this is the effect cadence has on p-value. It is a good sanity check. So I realized this, unfortunately, it was after running another data set with the same parameters. This one I had changed the gravitational background amplitude to hopefully see something. And that was when I realized that, oh, we're actually not varying time span. So then I, last night, simulated everything over again, varying actual time span now. And these were the actual results when you varied the time span for SNR. So you see there is at least it goes up, right? When time span is increased, that's a good sign. There's more data. We should hopefully have a higher SNR. There's still some big error, so I'll figure that out later. The reason the p-values are hidden and small is because they're pretty bad. The p-values don't seem to show any shape. I don't know why. I mean, the smallest one achieved is the highest time span, but there's really no trend. If you asked me to fit a line through that, I would draw a straight one, a horizontal one. So I'm not really happy with this result, but that's what we got when we varied time span. So my next effort was to vary the gravitational wave background amplitude. And so you're seeing there is trend in the SNR for sure. But there still seems to be no really good trend in p-values and all of the uncertainties or the errors and bars are pretty high on the p-value. So that's unfortunate, but we'll keep working on it. This is how far we got and at least we have some plots. So thank you. That's the end of our presentation.
Thank you. No questions. No questions?
I forgot.
Okay,
Yes.
go ahead. Well, I was trying to get,
Fair question.
I was,
It's a good
I
question.
was creating new plots for my
Yeah,
slides.
He had another, yeah.
Yeah.
When he returned was when everything started working, so.
We needed
We
pages.
needed him. Yeah.
So what is your expectation for how these things affect SNR, p-value, and what do you think will be the very next set of things you try?
Yeah.
Well, they should be decreasing and they're clearly horizontal, but.
But that's informed, so that's informed by the Simmons paper, that we have the analytical relationship for SNR to all of these parameters. And my plots for the SNR do kind of match up with, like the amplitude, it should be with the square of the amplitude, depending on, for the SNR. And it does look like it has a squared relationship, in my plots. The p-values, though, just don't really have any relationship. So my intuition is that if the SNR goes up with squared, then the p-value should at least be going down, because the SNR just moves you further along that curve for the exact same set of pulsars, right? I'm not changing the pulsars and doing the p-value again. So it should move us down. There should be a downward trend. I think, I mean, there easily could still be something wrong with the code. So I will definitely look through that and probably do some proof checks with like, if there's a way to do things even more simplistically so that I know like that a p-value I expect is what I get. Maybe I could do the actual, like the nanograph data set, like the 15-year, and see if I can reproduce the p-values that were reported for that, because maybe my p-value calculation just actually isn't correct. So that's my intuition, because the SNR does look good. It looks correct. Yeah, Colin.
Sorry, I'm not sure, but why are your restaurants slightly negative?
Oh, that, I told Tejas we would be asked that. So the SNRs are allowed to be negative because, like Tejas showed on, unfortunately I didn't think and I closed the slideshow, but there's actually a line written up here that I noticed that is the exact same thing. So this line of this chi-squared, like you do this fitting, the thing that's allowed to vary is the gravitational wave background amplitude, which would be this R here, the square of the amplitude. And so we allow it to be negative. This would be like the Harlings-Nast correlations, and this would be the data. And so you're allowing it to be negative to try and fit to this Harlings-Nast correlation, see if, you don't want to constrain it, like, from not being negative, and so we allow it to be, and sometimes it is. Especially if the SNR is really low, like if there's not really much correlation in the data, then it can definitely be negative. It sounds weird, especially because it's squared, yeah. Yeah, Kyle.
So with the optimal statistic as an estimator, you're linearly solving that chi-square function. And you make the implicit assumption that it has to be over the entire rate space. So it's unfortunate, but you can get negative amplitudes, and variances are always going to be positive. So you can get negative SNRs. If you have negative SNR, like -2 or less than that, so like -2 or -1, you're fine. It just means it's really late. But if you have SNRs of like -3 or -4, you're probably gonna have a problem.
Yeah. Thank you. Any more questions? Thank you.
Who's next? Does anyone have any intent to travel? They need to have, do it next. Yeah. Okay. You don't have to. Sure. All right, we're going. All right.
All right. I did this all by myself.
Oh, you put the
Did I? Wait, here, wait, exit out. We gotta put names on it.
Oh. Oh, yeah, I think you need a refresh. Oh, probably.
There we go. Ooh.
We are still
Damn.
back. Oops, wrong to share. Slideshow.
Lovely.
Awesome.
How do we want to do it? So that's a good question. We did.
I can start.
Yeah.
Fine. Hello, everyone. As you can see, we are the group that was trying to figure out the minimum number of single sources you would need to match to some extent the 15-year data or the Hellings and Downs correlations. So the process for that and what we're going to talk about today is, oh, not letting me, thank you. Yeah, just a quick introduction to what we were thinking about, what the thought process was, our methods, what we got out, and what we would do in the future if we had a bit longer. So, spoiler alert, you're not gonna get a number out of this. We will not be answering the question of what is the minimum number of sources, but we got towards it a bit. So if you want to find the minimum number of sources you would need and inject that number of sources, I mean, you gotta put them somewhere, right? So what we really tried to do was figure out where in the sky we would need to put one source, and then where in the sky we would want to put 2 sources, 3 sources, etc., but not etc., because that would take a really long time. So the real question we asked and are attempting to answer is, where are the best sky locations to inject these sources? So yeah, kind of like I hinted at here, the problem with this is the number of calculations involved and how fast that grows. So if you're gonna go through all of the pixels and test and compare them against each other, doing it for 1 pixel, like 1 source, is no problem. We can do that pretty quick. But once you go up to even 2 pixels, this takes way longer. So we called the pixels where we go to inject the sources hot pixels, and that grows as this function here. So like the number of combinations of pixels would be this n factorial over n minus r factorial times r. So that's for r hot pixels and just pixels in general. So we had to really decrease the resolution of our sky map. And yeah, we couldn't really put in a lot of sources because that just added on really quickly. And just to show how annoying this would be, I put together a little grid here that's only 5 by 5, and we ended up testing with 192 pixels. And like, so let's say we want to test a pair of sources, and we're having our first one at this black square. You've got to test this one, and then we got to test this one, and then we got to test this one, this one, this one, this one, this one. And just keep going. There's so many. Except for now, imagine there's way more, and then we got to do it again with 3, and we got to move this black square through each place. So that piles up very quickly, and we had a limited amount of time. So we only got results using 3 hot pixels so far. And the way we determined what those pixels would be is with a chi-squared minimization, as you can see here, and also on the board, same one that the last group talked about, where we have the correlations data from the 15-year analysis. We have that response submatrix that we built, the correlations covariance matrix, and here P is like the selected pixels matrix, in that you're taking a chunk of the matrix that corresponds to the pixels that you've selected. Should I keep going or just?
I mean, it's totally up to you.
Yeah.
Oh, I mean, I can do this one at least. So first, we just wanted to see the best and worst places to add a single source. And what we did for that was basically make a matrix that calculated like a tiered list of which pixels would be best to inject one source. So that one was a bit straightforward, a lot faster. So we got pretty good resolution here, a lot more than 192 pixels. And you can see here that that best part is over here with this yellow region here, which is kind of interesting because it's not in like the densest area of pulsars, but it's also not really where they're missing, so not so sure what to make of that, but it's a result. However, the issue is that the best pixel and the second best pixel are not necessarily the best pair of pixels. So continuing this analysis involved reworking things a bit.
Is that a real 15-year process?
Yeah. Yep. Indeed, it is. So now we decreased the resolution of our sky map by quite a bit, as you can tell, and ran the same concept, but for 1 pixel. And this is what comes out of it. You can see that it's in roughly the same sky area, but not exactly. Okay, so now when we do it for 2 pixels, this is a problem that we encountered, is that it takes 1 pixel and gives it a positive power and then is like, well, to cancel that out, how about we just throw another amplitude in there with negative power? Because the computer doesn't know that's unphysical and we can't just tell it that easily. You know, it's the procedure that Kyle just explained where it's that linear problem. So we didn't have a super straightforward way to stop this from happening. So the natural next step was to look at how our chi-squared value depended on the separation between the 2 pixels as we look across the sky. Do you want to talk about this one, Levi? You did it.
Yes, I'm pretty pleased with this. So on the last slide you saw the powers in those 2 pixels as found by our chi-squared minimization. And I was curious, like, is the second pixel that has negative power just kind of trying to reduce the error in each correlation? So I was curious, what does the actual difference in the pixel powers look like? And also, what does the chi-squared look like in terms of pixel separation? Are there any other chi-squared minima that maybe aren't the global minima that are vastly separated on the sky? But it's not really looking that way. It really is only very low angular separation pixels that have lower chi-squared, and you can see the 2 lowest are ones that just have a huge difference in their pixel powers. So clearly the minimization is finding that you can match the 15-year correlations the best by having one do a majority of the correlations and then a second one that can kind of add a little bit of noise to kind of reduce some of those maybe outlier correlations that it can't fit super well.
Hi. Cool. Yeah. So the next step obviously is to add a 3rd pixel. The search space for this dramatically increases because we are doing a brute force search. We're not doing like a smart search method. This one took, when I said, it's not crazy, but 80 seconds is not terrible. But it did find this solution as, the optimal choice for 3 pixels. And again, you see the same problem of just one, it just wants to put negative power to like cancel out any sort of noise from the first one. And it's not terribly surprising after seeing the second, or the 2 pixel solution. And so really, it seems like if we really wanted to do this like more rigorously, we would have to enforce positivity for all of the pixels, which requires you to use nonlinear fitting or do something like Bayesian MCMC, which maybe soon we will get results for that because it's not terribly hard to implement that. So we'll see. But yeah, it's not terribly surprising, but it did put another pixel right next to the other 2 pixels.
We're hoping to do another kind of pixel separation. But
Is that what you mean? Like this?
yeah, we're hoping to do this kind of thing for the more than 2 pixel case, but that would require, instead of doing pixel separation, maybe Kyle had the idea to do like an enclosed area kind of thing, so you could kind of get an idea for how far apart they are. You'd of course have a minimum of some number because these
These are as
These
close as-
pixels are of a like discrete size. I think these are 200 square degree pixels, so having all three right next to each other is not equal to the same area enclosed by the three vectors that correspond to those pixels.
Mhm.
So there's a little bit more math to do with 3 pixel separation chi-squared plot, but
Yeah.
another thing. Okay, I guess I'm. Yeah, so like Kyle said, a Bayesian approach might be interesting for this, so we can enforce physicality priors. The other interesting thing we thought about was maybe doing, so these are doing the actual like couple thousand correlations for the 15-year pulsars. And so this may be struggling with that because it's fitting pulsar variants where you have, you know, pairs of pulsars separated by the same angular separation at different points on the sky. So it's struggling a little bit with that pulsar variance noise, and so bin correlations could actually help maybe. So that's another thing we could try. And yeah, who knows? I mean, that's I think our future work is Bayesian and bin correlations maybe. Could also be a fun project for transdimensional sampling. So that's way off. So, no.
No, I definitely don't want to do transdimensional sampling and haven't wanted to do it like my entire PhD.
Yeah.
Why would I want to do something so cool?
Alright, so yeah, questions? Everyone back, ready, 1, 2, 3, back. Alright, Sean.
I wonder if you're doing like complexity analysis or model selection, or you're using pixels, but what are the degrees of freedom? It's like combinatorics problem.
So the number of degrees of freedom is the number of free data points that you have minus the number of models or model points. And so in our case, we had 2,211 pairs. And then those are our data points. And then you are fitting that to a model which has either 1 pixel, 2 pixels, or 3 pixels. And so it's just 2,211 minus 1, 2,211 minus 2, or 2,211 minus 3. So it doesn't end up contributing a terrible amount, which actually probably explains why we didn't find a minimum of the per degree of freedom, but that's how it ended up working.
Maybe I'm thinking about this too simply, but for the, like where you're showing the 2 pixels and moving the other one around, and that seemed to be like the bottleneck for a lot of, like, maybe it takes so long. So why, I don't know, would you be able to break it up into like quadrants and just say, like, if both pixels are in top left quadrant and top right, bottom left, or maybe, you know, half of the total is in top left and bottom right, like, cause then you can only have like 8 combinations or 6. But
Well, that's effectively like lowering your resolution, right?
like what?
Lowering your resolution.
Oh, okay,
It's lowering your sky resolution, which is
Yeah.
sort of the same. Like, we chose a lower sky resolution to make this problem more tractable analytically and to do it brute force, but, you know.
Yeah, I see what you're saying, yeah.
Conceivably, you could lower it even more to do exactly what you're asking, but, you know, if we could do it at this resolution, why not?
Yeah.
So in addition to trying to enforce some kind of positivity, pixel power, and putting this into optimization algorithms, stick the X where it is, something that varies everything rather than reinforce it. It would be really interesting to take your solutions so far and reconstruct what is the set of correlations that it's actually enabled.
So
What is it trying to validate, give that?
you totally can. The downside is that it looks kind of messy because I'm sure you've seen, like, for a single pixel, what the correlation looks like. It's kind of a mess. It's really hard to get any sort of interpretation out of it, which is why we didn't include it in this.
We taken, that's true for the raw pairwise correlations.
You're saying to like bin
Fit
them?
in against pairwise. Fit in against bin.
No, pairwise.
That's why the bin, I think, may help
It'll avoid moving the pulsar variant.
It would also be interesting though to do that and then look at the difference in the correlations over angular separation. If it's really just trying to, because our correlations aren't, we don't have the same number of correlations at every angular scale. So I wonder if it's trying to just fit where we have the most correlations. Like I'd be curious to see if the residual is at a minimum where we have the most pairs.
What was the first map we showed? It was a smooth map.
Yes.
This, believe, is the pigs.
This is theta. This is theta hat over the
Theta hat.
sky, or one pixel, I think.
Yes.
What's the color bar? Is that chi-squared or is that?
I think this is actually chi-square, right? Because those units don't work if it's not chi-square.
Yeah, I mean,
Those
we
have to be.
normalized it.
Okay.
But it would make sense because the bluest spot there seems to be right in the midst of the densest region of pulsars in the sky.
Mhm.
So it's where you're most sensitive. And maybe where you can fade the background, 1 pixel, right in the midst of all those pulsars. Any other questions? All right, nice work. Yeah, very nice.
Wait, come on.
Oh, yeah, practice.
Machine learning?
Too much stuff going on. There's so much stuff here. Can't see anything. No. How do I move this? How do I get rid of this?
It's not
Or up to top? It's not visible? Oh, okay.
All right, hello, everyone. We are a very normal team and our project was to.
Great.
It was to, there we go. According to the project description, build a machine learning inference pipeline for the gravitational wave background and check it against the standard answer. So the way we decided to break down that problem was to create a simulated data set so we would know what the right answer is. Then apply two different methods to it. One, the standard PTM-CMC method, and another, the machine learning approach with a normalizing flow, and then compare the results of the two. So to start us off, how did we create our simulated data set?
It's right
Yeah.
back.
Okay, so as just said, the first step was to generate the simulated starting from the NG15 dataset. And the first step after having imported the files was to zero out the original residuals, and we use the make ideal function. And you can see the comparison between the original time residuals and the residuals after the zeroing. The next step was to simulate the residual components with adding the measurement noise, the jitter, the red noise, and the gravitational wave background. And then last step was to add the simulated residuals to pulsar and nova arrivals. And there is the comparison between the original time residuals and the simulated residuals. And then after having simulated the boosters, we decided to use the feather files. So we converted the 67 simulated boosters to 61 feather files. It took forever. On my laptop, actually, I was able to convert only one user, but Kat eventually was able to convert 61 of them.
Yeah, the reason we lost 6 of them is just 6 of them had too much data and would kill my kernel because I would use up all the RAM I was allowed on the cluster. So I was like, let's just skip those.
They were too good.
61 is enough.
Yeah.
I feel my,
Yes, so
We'll get to that.
yeah.
Yeah.
We'll get to that. Okay, the next step was to import the simulated pulsars and run an MCMC analysis on them. So we had to import them to Enterprise, and with Enterprise, we had to construct our model. So it was the timing model plus the white noise plus the red noise plus the common red noise. So for the white noise, it was fixed per pulsar. That was just through the back end. We had a noise dictionary from the NG15 dataset analysis that we used. For the red noise, we decided to vary them. We tried varying them and then also fixing them with the back end. But when we did that, I don't know, it just like didn't look good. It wasn't right. So yeah, we just decided to vary it. For all of the amplitude and the gamma for both uniform distributions, you can see our priors there. For the red noise, that was also per pulsar. So each pulsar has its intrinsic red noise. And then the common red noise is shared across pulsars, but we're using the common red noise instead of like GWB because when we ran our analysis, there's no I'm bad at describing it. There's no correlation between each pulsar, I believe. Hopefully I'm saying that right. I don't know. But so we did that, applied each the model per all 61 pulsars. And I also ran it with the feather files compared to like I was using Parntim the whole time, basically, and then yesterday I did feather files and it was like so fast, it was crazy. It took like 30 minutes to import them to like 2 seconds. It's crazy. So then I had to set up my PTM-CMC sampler. So we had 61 pulsars, so our total number of dimensions 124 because we have the amplitude and gamma for each pulsar for the red noise. And then you have the amplitude and gamma across all the pulsars, which is 2 dimensions, so a total of 124. And then you just have the enterprise like the log likelihood, the log prior, and then you start with the covariance matrix. So each dimension or each dimension is independent of one another. Yeah, so you start with the diagonalized covariance matrix. And so initially when I was running them, it was like not looking good. So then I talked with Nima and it was a horror deal. We like switched from PTMC to something else, and then it wasn't working. And then we had to ask Claude for help to write a whole class to get these jump proposals because we didn't have jump proposals, which from what I understand, it helps balance the sampler when it's searching over the parameter space because we have like 122 dimensions with respect to the red noise, and then the common red noise is only 2. So like, from what I understand, it doesn't really search over the common red noise as much as we want it to, because those are the posteriors that we're looking for. So it kind of helps it weight it towards the common red noise. And so then we had to run the sampler. That was my starting point. We just took random starting point based on the priors. That was for the common red noise. And then we ran 1 million steps. And then we have these weights, which basically describe how we want the sampler to search over the parameter space. So the AM and SCAM, there's also a bunch of more weights, but they're all defaulted to 20. So the AM and the SCAM weight are weighted higher. Or no, sorry, the SCAM weight is weighted higher because it's not as computationally expensive. Because it's basically a single direction in the parameter space that adjusts the covariance matrix. And then the AM is a search over each direction in the entire parameter space. So that's more computationally expensive. And then we also took these values from a tutorial that we were following. So they probably have a more sophisticated reason than I do, but that was my reason. And then the differential evolution doesn't actually adjust the covariance matrix. From what I understand, it takes two previous points in the chain, constructs like a vector, a difference vector, and then goes in that direction. So it doesn't adjust the covariance matrix, I believe. And then these were our results for that. So our injected are the negative 15 and 13/3. So the red is the injected from the simulated pulsars. And yeah, we got pretty good values, like negative 15.44, 5.19. Like, I think that's pretty good compared to some of the other ones I was doing. Yeah.
All right, now for the other method, the normalizing flow. So we mostly followed this paper, so yeah. All right, so the idea of a normalizing flow is it's some sort of neural network where you say, I've got these likelihoods and I want to find out what the best posterior is, do a bunch of stuff to figure that out for me. Well, what that stuff is inside of the network, you have a series of individual transformations that get applied to subsets of the data. These are affine transformations, and these are basically transformations that preserve parallelism, straight lines, like combinations of your basic transformations like rotations, squeezing, whatever. So you have a series of those that get applied to the data to see if it can mold this side into that side. And then it figures out how bad that is using a loss function, which uses the Kolbach-Liebler divergence, how do you say that? Basically, the goal is to minimize this function and find a way to transform that into that while minimizing the loss function, or alternatively maximizing your evidence lower bound. So each, as the network is training itself, what it does is it tries a series of transformations, checks the loss, then uses gradient descent to find a new set of transformations to try, and keeps doing that until the loss is low enough to an acceptable level. And then it says, hey, I found a transformation for you. And a neat thing about this neural network is that it produces a bijective function. A lot of neural networks kind of reduce the dimensionality of your data to give you a result, so you lose a lot of information along the way. But from here, you can run it forwards or backwards to go from one to the other. That one is called a normalizing flow because each step along the way preserves the normalization of the data, so you're saving probability. Yeah. All right, so the way this works kind of in a workflow sense for code is you start with feather files, and the reason you want to use feather files instead of par and tim files is because, as you mentioned, they're a whole lot faster. The reason they're faster is because these are pre-computed binary files that don't care about what language is being used to read them. So if you look into the par and tim files, you see you can scroll through, you can read it. It makes a lot of sense. It's a human readable file. But that means it's slow for a computer to read in. Because when a computer reads in a file like that, it reads line by line. Each line has a single data point from each column, so it has to read the line, put each thing into the data for each column, do the next line, and so on. And that iterative process is very, very slow. Anything iterative on a computer is going to kill your time. So what a feather file does is not only is it a binary file, it also moves it so that the columns get read each one at a time. And that's a whole lot faster than doing row by row.
So that's why you can go from taking 30 minutes to load all your pulsars to like 5 seconds, even though it's the same data. So once you read in all your files, you need to write out what your likelihoods are, tell the code what your loss function is, and then give that to a normalizing flow. And these steps are derived from an example that was paired with that paper that we were going through. That's in Discovery. So ours had 16 layers and 1,000 steps total, where each step had up to 1,024 iterations of that checking the loss loop. And so the training overall took 20 minutes. And then finally, we sampled the resulting posteriors to see what it looked like and came up with this. So we, again, the injective parameters are within kind of our 2 sigma contour, at least. I think there's probably a little more going on with the red noise than I understand. But hey, it's in the circle or in the ellipse, so we're good. Okay, so how did the 2 methods compare? Very well. It's kind of creepy, actually. Yeah, so as you can see, both methods ended up computing approximately the same values. So you might be asking yourself, why would you choose to use something like a normalizing flow instead of just the classic other methods? So this actually, I don't think provides that much benefit for this particular use case. One, because the data set is pretty small compared to how big data sets can get. It's only about 2.5 gigabytes total, the whole 15-year thing that you can download. And also this shape right here is still pretty much a Gaussian. I mean, a little squeezed, but so normalizing flow will help you more if this shape is not kind of a standard shape, like say if it was a banana or something. And it was faster, I say with an asterisk. I mean, it only took 20 minutes. But also, we ran out on a GPU versus PTA CMC on the CPU, so I don't really think that's a good comparison. One benefit I do think it would afford you is if you want to rapidly test a whole bunch of different models, and just to kind of vibe check, see if something is working, and then put it through your more robust code. That's all I have to say about that.
Sorry, it's probably a dumb question. I don't understand for the normalizing flow, but you don't know beforehand what the ground truth and posterior distribution is. So like what is the loss function comparing the predicted posterior distribution is?
Let's see. I'm gonna be honest, I don't fully understand it.
Yeah, I don't
You got a
remember.
question for us?
I don't like that, but the stochastic variation of it. Normalizing flow is a tool inside the stochastic variation of it. You have this whole setup where you're trying to find what is called a guide. And guide is a posterior that you're trying to reparameter. Let's say you want to say the posterior I'm looking for looks like an inverse gamma with some unknown inverse gamma value. The whole objective of machine learning is to optimize those parameters of inverse gamma. So they are approximately posterior, as much as it can.
So that means that you have to know your posterior beforehand.
No.
But then it's using the likelihood, so it still requires that you have a function that computes the likelihood. And you have a prior, so it's able to use the unweighted posterior, likelihood and prior, and then move around and distort that normalizing flow to approximate the shape over the parameters of this function.
So you're just sampling the posterior and evaluating what the might be sampling that posterior is basically.
it's not sampling in the sense that we normally do CMC, but it's getting measures of the unweighted populator across the parameter space to flex that normalizing flow and get the shape to be as approximately as close as possible. All of this is built in an effective proxy, so we should draw samples immediately.
So it's like you come up with a guess of what it looks like and you see how well that's supported by the data. And then you try another one, see if that's better supported and so on.
Thanks, sir.
Yes.
Silly question. For normalization, it shows the layers and shapes per number. Is that like same thumb rule like in CNC? How you do the number of layers and shapes? Is there thumb or rule of thumb or something?
They're probably, usually to choose those numbers, you kind of just play around with it a bit.
I don't think so. It's a lot of guess and check.
Yeah.
Are there any standard rules of thumb for the depth of layers, number of layers?
If you're dealing with more than 100 dimensions, you need, at least, I would say, 32 layers for your flow. It depends on your architecture, but you can, more dimensions, more complexity for your flow. It gets to a point where, it takes a few seconds to understand what was happening. So it breaks at some point, in practicality breaks, but on paper, it never breaks, but on the practice, it can break this dimension. But with these ones, you can, if you have a couple of hundred, with, I would say 16 layers of neural network, a few thousand neural in each layer is more than enough. But it all depends on the software you're using.
Yeah, there is a lot of checking because you want to make sure you don't make it too powerful because then you just start overfitting your data, but you also want to make sure it converges. So just play around a bit. We stuck with the numbers that were inside of the sample notebook.
It's a bug, and I will submit a PR for this. The newest version of Enterprise doesn't seem to work with whatever PTA integration you were using. So it should not have been as painful and not have involved flood. It's a slicing issue of the parameter group. So, yeah, so hopefully that will get it.
Great, yeah. Special thanks to Nima for helping us out a bunch.
Yeah.
Very last question, is
Oh, yeah.
I want to know, is the normal gathering start off with that if you wanted a two-dimensional posterior, you start with two-dimensional gathering, is that right? Like, you said the dimensions, or you said it's by diagonal constant, and it's dimensions to purposes. So that means you start off with a two-dimensional gathering and you try to fit that to two-dimensional.
Yeah, you're basically just finding a way to deform it so it looks like something else and then seeing how well that something else is represented by your data.
I just wanted to make sure.
Good work, everyone.
All right.
I think Ron will last.
Yeah.
How do I present? How do we present?
Screen share.
But it doesn't allow me to. Am I on the right meeting?
The right meeting.
Steve, I am unable to share.
Your Linux.
Yeah,
I looked at my computer.
all right. It's fine.
Yeah, the sharing problem seems to be with Linux.
Okay.
Oh my goodness, which browser? Okay. VIPER, there we go.
Yeah.
I have so many windows open.
Can you share full screen?
Show. Okay.
Yeah. Sure.
Hello, everyone. So we were testing the non-Gaussianity of the stochastic gravitational wave background group. This is, I think, also as you all saw, kind of the corner of Dower, the screaming and crying. It was a fun time. So we're going to talk to you a bit about our process and the many different avenues that it took and what we learned. First of all, some background. If the stochastic gravitational wave background, which we usually assume to be Gaussian, if it was Gaussian, the Fourier coefficients would be drawn from a Gaussian distribution. And if so, the excess kurtosis would be 0. Excess kurtosis just being the kurtosis of your function minus Gaussian kurtosis. If it's not Gaussian, we will have a non-zero excess kurtosis. Easy. The idea was that by changing the number of loud sources excised from the data set, we would be able to see excess kurtosis either go down or go up in the resulting background. We would imagine that the more loud single sources we had in each frequency bin, the more kurtosis we would have. And the more that we remove those extra loud sources, the more Gaussian it would look. So this is the kind of 4-point correlation function that William Lamb's most recent, is it his magnum opus or is it just a really good paper?
It's his magnum, it's finishing here.
That's what I thought. So William Lamb's magnum opus was kind of our Bible for this. And he wrote this 4-point correlation function describing how one might quantify excess kurtosis in the gravitational wave background seen by the pulsar timing array. So it looks really messy, but a lot of this is due to the fact that it's being observed in the pulsar timing array. And it all is, furthermore, all in terms of just the number of sources per bin, the amplitude of those sources in that bin, and the mean frequency of that bin. So it all reduces pretty well. And we can get this into a nice little approximation of this. I have to go through all the oopsies. So the 27/7, we are not going to have to worry about because our gravitational wave background, we are not observing with the pulsar timing array, which is a key distinction. That's also a great reason why we don't have to worry about things like the window functions. So this is the equation for excess kurtosis that we will be using. What was secretly inside that was an implicit sum that we found out about on Wednesday. That changed the way that we had to calculate this in a bit of a headache way. So we went over this a bit in the holodeck tutorial, but holodeck that makes a universe, it makes a universe like this. It creates this data cube that is distributed on frequencies with an axis for redshift, axis for total mass, and an axis for total mass, for mass ratio. And each of these grid cells in the cube, it populates statistically. So it's not a determinate amount of sources that exist, but one that we have to extract from the statistics of the realization of that universe, or averaging them over many different realizations. So this just meant that we had to be careful, mostly, about the information we were extracting and how. The idea was, and this seemed like a really simple and low-hanging fruit at the start, was we would just construct a semi-analytical model in holodeck
we would just extract the relevant values because surely that will be easy. And then we will calculate excess kurtosis, and then we'll have so much time to do all these other bonus projects and bonus inferences with it. These are the plots we were mostly trying to do a spin on from William Lamb's paper, where he used number of sources. We wanted to look at it as a function of the number of single sources we were taking into account in the data. I'm making a note here that these are using what we called LambDeck, because William Lamb made a tiny version of holodeck that suited his needs. This is LambDeck. It's very nice. It has a discrete amount of sources. He's having a very pleasant time. This is holodeck. Too many sources. A lot of the numbers we were getting to extract, the first thing that roadblock we hit was it was an incredibly unphysical amount. Trillions and trillions and trillions of binaries. Did not make sense. 10 to the 15 per bin. Okay, we changed the hardening parameters. We changed some of the inputs to the model. Okay, now we're at 10 to the 8 per bin. We're still really high. So here's the screaming, crying, throwing up circle about holodeck. This also means that we were not using holodeck as intended, is one of the things we also found out. Holodeck, tool as intended, is designed to study the effects of black hole physics and input in different models of black hole physics on the resulting gravitational wave background. What it is not designed is to replicate and study the Gaussianity of that background. This is where our work begins to deviate, and we can really understand why LambDeck came into existence. LambDeck, you can just put in the number of sources, you can just specify these things, specify the parameters you are interested in to calculate excess kurtosis. But drawing them out from a statistical population for a simulation that's not worried about replicating Gaussianity turned out to be slightly a nightmare. We'll pass it off to Nathan to talk about what we actually found.
Cool. So wait, pointer. This is the equation that Martine had showed us earlier. Like she said, it's summing over a lot of that entire four-dimensional grid that she showed. Well, 3 dimensions plus the frequency. Frequency ends up as a delta function, so we don't have to sum over that one. So what we had to calculate was this a to the 4th here, which is the gravitational wave strain amplitude. And that was something that we can calculate deterministically for each of our bin centers. So it's just, I don't think we have the equation actually in here, but simple enough equation once you have mass ratio, redshift to get the amplitude for each of the bin centers that holodeck creates its gravitational wave background on. There's also a nice function for this number of sources per bin. It is the mean number of sources per bin. So when holodeck actually makes its population, it is drawing from a Poisson distribution with the mean at this n. But from there, we can calculate this equation. And what we get is, do this for each frequency that we're looking at, and we can get this function that is similar to the one William made, this one here. Excess kurtosis is a function of frequency. And you can see we match him in some respects. We increase as we increase our frequency. Yeah, kurtosis increases, excess kurtosis increases as frequency increases. That's great. There's some differences though. If you look at the magnitude on this graph, his excess kurtosis is 3 at the highest frequencies. Ours is, for these parameters, 10,000. We also have some shape differences. We have a steeper increase here, and if we look at our low frequencies, there's like kind of, so you can't see the excess kurtosis at low frequencies compared to at high frequencies. On his, it was, you could see it even at the scale of the high frequencies. You could see that there's still some excess kurtosis at low frequencies. So why doesn't this look the same? What went wrong? So let's actually look at for each of these individual lines. This is something that we made in the holodeck tutorial. Each of these individual lines is a realization. and we're plotting our characteristic strain over, as a function of our frequency. And what we can see here, at high frequencies, this is a very, very spiky graph. It doesn't really look like a Gaussian. So we really shouldn't be expecting to get low numbers of excess kurtosis. We should be expecting to see something that is very non-Gaussian, because I look at this and that looks very non-Gaussian. So let's kind of reframe our question here. Instead of saying what went wrong, why doesn't our stuff match Will's? Well, we used different things than Will did. We used completely different software packages with a lot of differences in it. So what about what we were doing in holodeck caused this insane non-Gaussianity that we're seeing here and in our excess kurtosis? So let's look at the parameters we use. So the one above, we had used the phenomenological hardening model. So we're not only using gravitational waves to have our binaries get close together, we're using other galactic effects. Using our galaxy stellar mass function, galaxy pair fraction, galaxy merger time, and MM bulge from the holodeck tutorial. Originally, these had been just kind of like there's default values in our SAM. So if you just say SAM shape equals 30, that gives it some default values. Further down the holodeck tutorial, there are some default functions. So we were using for the graph above, those default functions there. I was using in this case a 50 by 50 by 50 grid of mass ratio redshift. This does not change the extreme values of any of those quantities, just how finely you cut them up. So I'm using a little bit more than we used in the holodeck tutorial there. 20-year observation time to spend 20 years in nanograph. And what we saw was 10,000 as our highest excess kurtosis. And we could change these. Move to gravitational wave hardening, move to just the default values from the semi-analytic model, smaller grid, lower observation time, and we get these graphs, which you can still see very, very, very spiky here at high frequencies. And our excess kurtosis now is at 10 to the 7, which is very, very high. This is something, so we all three of us calculated this almost semi-independently, and Martine especially went through it like very, very carefully to make sure it made sense. So even though it is 10 to the 7, I'm still kind of thinking that we did that calculation part correct, and the problem was in the holodeck parameters that we were using were unphysical. I think Sam will talk about later some of the things he found in that, but just as a reminder, a comparison between these two. When using our more physical params, we got excess kurtosis around 10,000, very, very spiky at high frequencies here. And then we changed it to be less physical, and it got to a much higher max kurtosis there. And these are.
So it was a learning experience, and we learned, first of all, that holodeck doesn't have great documentation. And one of the reasons why I'm saying this is because I had to go through the code to find out that one of the reasons why we had so many sources is due to the insane priors that holodeck puts on the population. I'm saying insane because this is the model configuration that I'm about to show you, but the actual holodeck model parameters, the total mass of your binary spans from 10 to the 4 to 10 to the 12 solar masses, which has no reason to be a PTA signal. 10 to the 4 is, I don't know, it's Lisa, but not even. So mass ratios are fine, but redshift were spanning from 0.001 to 12, which again is unphysical. So that populates your source background with many of objects that basically have no weight at all. So what I did is that I went through the configuration again and I changed this a little bit. And now they make more sense. So we tested if using a GW hardening only or a phenomenological hardening would change things. So as you can see, it does change things a little bit. It puts the number of sources to be a little bit lower. And then these are the number of sources that you get for, as a function of mass ratio for your first frequency bin, meaning 1 over year, which is the most populated one. So now they make sense, not 10 to the 15, yay. So 10 to the 4, that's good. And this is the amount of sources that you get per frequency bin. Now, at least the calibration has been corrected. So, but
the cool thing about this is that now we can test kurtosis as a function of excise sources in the following way. What you can do is that you can simply see, well, what if we remove the loudest sources from our background, just like holodeck told us to, and we see what happens to the kurtosis. So first of all, we thought that as we excise more and more sources, we would get higher kurtosis, but in reality, it's not like that, because the way it works is that as you remove the loudest sources, your background becomes more and more evenly sampled, let's say. The sources do not contribute as with such a difference in power, so they behave properly. So what we did is that we got those HC, this strain, and then we plotted them. And as the number of sources increases, we get something more and more Gaussian. And this is our kurtosis. Yay, we did something. That's great. So now, as you can see, we start from a 0 sources excised. This is the whole data set. As we remove sources, we kind of seems to converge to a Gaussian something. So good. Okay, so this was better. This was not. So this didn't change at all. So we tried to do the same thing again, but now with the new model with the good parameters. So just both of my colleagues already mentioned this, but this is an approximation that has been done by considering a distribution of sources, each of them contributing with a random phase. So you do all the math and you get this. So this should be reasonable in theory, but in practice, we didn't manage to make it work. I just want to mention that it could be an effect of the number of sources, because as you increase the number of sources, this drops down, because this goes as 1/n. But then what do you want to do? Do you want to be more physical? Do you want to, I don't know. I have no idea about why this doesn't work. So we thought, let's change paradigm. So if holodeck isn't able to produce the Fourier coefficient for us, how about we do it ourselves? So we basically reproduce what holodeck does. We set the number of sources in each frequency bin with the average one that holodeck gives us, and we sample per each realization a certain number of sources per bin using a Poissonian distribution. And then we associate a sinus of the random phase to them. And so each source contributes a strain HI. We are talking for that specific frequency of our frequency bin with a phase phi I. And we randomize this phase with a uniform distribution. And H naught, the formula for H naught comes from a paper by my advisor. And yeah. So now what you do is that you have this, you sum them all up for each frequency, and you can do a little bit of algebra, use the cosine of alpha plus beta formula, and you see that these are your Fourier coefficients. So the Fourier coefficients really tell you what is the distribution of your phases over the different universes. And you want to check how are these distributed. And you get this. So as a function of frequency bin, you have less sources for that frequency bin, but each of them contribute more. And so the distribution of your Fourier coefficient tend to be more and more, say, spiked. And but then this would tell you, wait, but what is this? Is this a uniform distribution? Is this really a Gaussian? You would expect that at low frequencies you retrieve Gaussian distributed coefficients. So there is this thing I found online, which allows you to basically scale this to an actual distribution. This is called a Z transformation. And there you go. And you get something that seems to be working, I guess. So as you can see, we seem to retrieve the Gaussian distribution. So that's good. And finally, like the MVP from this work was to also do a QQ plot. A QQ plot is simply how
how the percentiles of your distribution compare to the percentiles of a Gaussian, normal Gaussian distribution. So this is a quick test to see if there's any deviation from Gaussianity. And so there it is. This is the sample kurtosis of your distributions as a function of frequency. And these right here is your plot. So problems with this? Again, incredibly high excess kurtosis for some reason. And this thing, I don't understand it. I have no idea why this doesn't work. But yeah, we did something. We used holodeck mostly wrong for the majority of time, but then we found out that maybe we could use it in a different way, and the way we used mostly holodeck forwards to do this. So yeah, that's it.
Can you go to the actual plot like this, areas three?
This one?
First one, first.
Williams.
All right. Yeah.
In the low frequency range, also there is a like, are we here to? Yeah.
All right, it's not. You would expect it to be completely monotonically
Yeah.
increasing, but it's not. I mean,
There is a reason.
There is a.
There is. You might have to read the paper to find the reason. It is explained in the paper. I think it was dominated by something at low frequencies and something else at high frequencies. So that's why the shape is different. I don't remember exactly what the low frequency was explained by.
What would be the very next thing to cross-check some of the different methods that y'all were employing? What's the easiest way to get them to compare against each other? Would you use holodeck? Would you use lambda?
I think if we were to continue using holodeck, the upshot of everything we've discovered is that holodeck doesn't produce a Gaussian background, which is like being, from my understanding, is being upset that your wrench doesn't make a good pillow, right? It is not the tool it was designed to do. I think if we were going to actually analyze the statistics of the gravitational wave background, using lambda would be a far better tool. That actually allows you to have direct control over those parameters. Yes, it's more of a toy model. I'm sure that there could be work done to flesh it out, but holodeck doesn't produce Gaussianity. So either the next step would be either. I did this a little bit, and I have a bunch of screenshots of plots that I conjured up yesterday of analyzing how different model input parameters affected that kurtosis. Kurtosis only went up. I tried different hardening methods. I tried different distances, different ages, lifetimes, different input mass functions, and I went through kind of line by line. I didn't go through all of them, but I got some excess kurtosises of 80,000, 120,000, just based off of varying one of these things. Kurtosis never went down.
I guess a few checks that you could do would be regarding this, to answer your question also. First of all, we really need to go back to the paper and understand what assumptions were made in order to have that approximation, because it seems to come from the same process that we in the end did ourselves. So this last excess kurtosis one. So we would need to cross-check this, because I don't know, like our kurtosis is very spiked. So could be for many reasons. Could also be from the number of sources. And maybe you're so few populated here in this part that you can't really make a statistic out of it. But still, I don't know. I have no idea. Yeah.
Because using to calculate the excess kurtosis from the parameters output by the holodeck semi-analytical model is what is producing these crazy amount of excess kurtosis.
So, calculate your trend time with all of it
Yeah,
over how long ago, but
We've been using 100.
well, depends on what part. Here, 1,000.
harder.
Here we have 1,000 realization.
Well, that's not enough. You get it, that's why we'll never repeat it. Even if you don't find the random or mobile, 1,000 drugs, it will never be there.
So,
Combination is by following model parameters, there's variation inside of that level. You start with everything, start on 3 parameters. So you've got the realization, which is the post combinations. And then you've got a different combination of the holiday model.
yeah,
1 in 4 of them, 1 in 4 of the other. Backward, then distributed across all those 2 variants, so it will be out.
yeah. I think also it's because like this part of our study, this age, we base, I don't know, I'm not sure about what we did here because just by the fact that, where is it? Where is our background? Yeah, here. You see like, I mean, we are comparing power here. We're not doing a Fourier decomposition of each single source as we're doing after. So we can't really be negative. Could it also be that? But not really in reality, but.
I, so the reason I'm asking is because I really got the fact of it.
Yeah.
Ah, that's nice.
It's,
Good job.
I do it every day.
Yeah, so what,
It's very difficult, maybe probably work for everything. So that's probably.
Yeah.
That is definitely a lesson learned.
Understated.
I was thinking about putting in a meme here of like, you know, like a headlock or anything, but I was like, I don't know if that's too violent because I really felt like we were trying to force holodeck to do something it didn't want to do.
Well,
More comments, so because holiday allow you very higher level parameters. You may get a combination of parameters that produce only 10 sources. And that will be my way together. And then you're gonna get a parameter that you're gonna get a combination that produces 10 sources. That's definitely together. So it will, all the answer whether it's not Gaussian, Gaussian, it's not Gaussian. But, you know, if the harder part is actually trying to see what happens, which we have this big agnostic model, that it has 10 sources of part of that, 20 sources also part of it, something like that. And then you go to inference and you try to account for all of it at the same time, and then see if, assuming Gaussianity, I think the product makes it good. But as they call it, produces both, I would say. So there are combination of parameters that will only give you a few sources. And then the other will give you maybe even 100 or 300.
yeah,
It's not the answer is Gaussian or non-Gaussian, the answer. If you want it to be super realistic, I'm not sure how they did it quite a way, but I don't think the answer is just very simple.
That makes sense.
Yeah, my interpretation of this was that what we did in holodeck gave us a lot of non-Gaussianity that you can see here. But I think, I don't know how, if we really went into and broke it down and found parameters that made more sense, then it probably would look more Gaussian. I don't think any of us really found those. I mean, Sam changed the masses and reproduced this with, I think, I'm not sure if he used the same other things. I think the next step for me would be really lean into what do we change in holodeck and what should we have as physical values, and then through in those physical values, what makes things look more Gaussian, what makes things look less Gaussian. I also wanted to add here, nothing we're doing in this calculation depends on the number of realizations at all. because we're using the true mean of the Poisson distribution that holodeck draws from. So, like, we don't even end up drawing 100,000 or 100 realizations from holodeck, because we have the true mean number, and the amplitude of everything in our grid cell is a deterministic function that we can just calculate. So we have the true mean of the Poisson distribution that holodeck draws from, and analytically calculated amplitude. And so we don't, there's no different realizations.
But you still need to do a combination of factor and probably.
Yeah, we need to find the holodeck combinations.
Very many, because if it's not, you will always have a fail, and you will always be counted as an unreality.
When you're talking about parameters, you're talking about like make the hardening model,
Yeah.
stuff like that.
Yeah, that's I think what we need to.
I don't know if we can get more robust than what we did have. We had, if there was an input parameter into the semi-analytical model, we had it assigned as something that we thought was the most physical. I'd be interested to see what model parameters that you use to produce a Gaussian result, because when I was trying to vary those, I did notice that Gaussianity only either stayed at that 60, 10 or 10,000 mark, or went up to 80 to 120.
I think, I had the most insight into the journey that this group has been on. It's been quite a journey, so congratulations on everything that you did to explore this problem.
I think we have more questions.
Is there one more question? Go.
So the one suggestion, suggestion is to look at the MU15 posterior parameter. It could be used for that, and use that as a case study to look at. The other one, so you're saying that you're using the like rate in each grid cell, and you're doing the analytics under that. That might cause a problem for, if the rate is 10 to the 6, a little bit, you're gonna more or less simulate the 6 or 5. If the rate is like 0.2 in one of these higher frequency or higher amplitudes.
The rate being the merger rate, or?
The rate being your grid, and you can see.
This. The end?
Yeah, exactly.
Oh, okay.
There's no guarantee that doesn't enter if you're not taking Poisson growth of that rate. You might be accidentally enforcing the public and let a source at a really high amplitude. It's like a 1 in 10 chance you could actually get a source there that's contributing. And so this might be impacting the results when we accidentally populating like these fractional sources that are contributing.
When we analyze, and I'm so sorry to respond so quickly. When we analyzed the number, the array that was put out when we did our number calculations, every part of that array had some order of magnitude that was greater than 3 or 4, usually around. By the time we did different semi-analytical model inputs, this is how we rested on which ones we thought was most physical. Is we got the most physical amount of sources, because the defaults were giving us 10 to 15 for frequency bin, and we kind of took our 10 to 8 per frequency bin and walked away. So we're not having like a 0.1 source in any bin. If anything, we have too many.
Super low rate.
Yeah.
Okay.
One of the ideas that we really had was to avoid that exact problem, was to just scoop off the top, the loudest sources, and analyze and construct from that single source background a new kind of loud background, and look at the statistics of that. What put a roadblock and injunction in that is we had to revisit how we were calculating everything and crash out for like 5 hours about it. And so that idea kind of got the brakes pumped on it, as we weren't really quite sure how to incorporate that with our process going forward.
Yeah,
really good, very good. Congratulations. Thank you, man.
Great. All thanks for that. Finding that. This should not go to any before.
Okay, I'm the one now standing between you and getting delicious banh mi lunch, so I'll try to be as quick as possible. Thank you, everyone, for participating, for helping, for making what I think was a great summer school. I hope you all learned a lot. And I hope that any confusions encountered or like difficulties encountered, I hope you look back on it as friction that was good because it encouraged you to go and explore more. And friction is good. When answers come too easy, it doesn't feel like you've earned it. So I know this has been quite a journey for some of the teams, and even just getting the software installed and making various things work. In particular, I know there was, well, you encountered some friction along the way. You looked at some things that seemed on the surface quite simple to solve, but those edge cases led to many more interest and difficulties encountered. I know there was one particular piece of software that got lots of references as being quite challenging to install and to do. But I promise that as time goes on, you will look on PTA Replicator and other pieces of software as having full control over them. Okay, so you'll look back on the experiences you had this week, the last 2 weeks, and you will have the expertise that you wish you had these last 2 weeks. So I did want to give a quick shout out to all of the lecturers and the speakers who donated their time and effort to make this a successful summer school. So let's please give them a round of applause now. In particular, I'm the one standing up here, but I want to thank my local team, my students, my postdocs that really made this successful. So please, let's give all the students there and postdocs. And unfortunately, they're not in the room at the moment, but Juliet Traub and Dawn Pickard have been instrumental in making sure that we have very tasty lunches and that you had breakfast bites in the morning and that those were all cleared away and the room was nice and tidy. So none of this would have worked without Juliet and without Dawn and then without all of you making this a success. So thank you very much for coming. And I want to get a week 2 version of this photo as well. So whether we do that right now or I leave you alone to get lunch is entirely up to you. I think let's get some lunch, shall we?
Yeah.
All right.
Yeah, okay, we have banh which Bloom here has never had a banh mi. Oh, it's exciting. Okay, so banh mi's are a fantastic outcome. An unfortunate result with French colonialism in Vietnam. We have French baguettes with Vietnamese cuisine. So we have chopped steak banh mi, and we have lemongrass chicken, and there's also rice bowl and vegetarian beef. So